in the previous class. Today we will talk about state reduction and assignment. Now there are two things. One is analysis. That means a given circuit is there and we are going to analyze that circuit. From that circuit we get state equations, we get state table, and we get a state diagram. So the end is state diagram. Another is circuit synthesis. If you want to design a circuit, what do you do? So what we have as a given is a set of specifications, and in using those specifications we can draw the state diagram. That is the first step. Then from the state diagram we can draw the state table. Then we can reduce that state table, give assignments to that state table, state assignment, then write the state equations, and then draw the final. The end of that is, the end fruit of that design will be a sequential circuit. So what is a design? If you want to design a clock sequential circuit, what all is involved in that? So first thing is, we are given a set of specifications and we draw the state diagram using that specifications. So let's have a state diagram. This is a state diagram and the states are given the name A, B, C, D, E. So if this is a dash, this means X, Y, that means input, and on the right hand side it is the output. This is the state diagram of a given set of specifications. So we will draw the state table for this one. What is the state? Present state. A, B, C, D, E, F, and these are the present states. What is the next state? For x equal to 0 and x equal to 1. And what is the output? This is the way you have to make the state table when you want to do state reduction. Okay? We talked about this in the previous class also. There are two ways of making a state table. So whenever you want to look for state reduction means if you reduce the number of states, it may or may not lead to the reduction in the number of flip-flops. And if flip-flops are reduced, that means you are going to get a smaller circuit. So for x equal to 0, it remains within the same state and output is B. For x equal to 1, it goes to state B and output is 0. From B, for x equal to 0, it goes to C, output is 0. For x equal to 1, it goes to D and output is 0. From C, for x equal to 0, it goes to A, output is 0. And for x equal to 1, it goes to D, output is 0. From D, for x equal to 0, it goes to E, output is 0. For x equal to 1, it goes to F, output is 1. From E, for x equal to 0, it goes to A, output is 0. And for x equal to 1, it goes to F, output is 1. From F, for x equal to 0, it goes to G, output is 0. For x equal to 1, it remains within the same state, and output is 1. From G, for x equal to 0, it goes to state A, and for 1, it goes to state F. So this is the state table for a given state diagram. Now, is the state reduction possible? When state reduction algorithm or statement says that if from a given state, for a given input, you go to the same states for a given set of inputs, then you can remove one of the states. From A, you go to A and B for x equal to 0 and 1. ये भी कोई A B में कहीं कोई जा रहा है नहीं. From B it goes to CD, CD में भी कुछ नहीं जा रहा. From C it goes to AD, AD में कुछ जा रहा है नहीं. From D it goes to EF, EF में कोई और जा रही है नहीं. From E it goes to AF. So you can see that these two states, for x equal to 0, it goes to the same state A and it gets the same output. And for x equal to 1, it goes to the same state F and gets the same output. So if from one state it goes to the same states for a given set of inputs and get the same outputs for a given set of inputs, then we are going to eliminate one of those states. Let's eliminate G. Eliminate. So that means replace G by E in state table. Wherever you have G, replace by E. So we get this. So if you see this, your table now reduces. This is the present state. A, B, C, D, E, F. What is the next state for x equal to 0 and x equal to 1? A, C, A, E, A, E. Because G has been replaced by E. B, D, D, F, F. This is, what is the output? Zero, 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 1, 1. Now can you still find out that can you reduce the state table further or not? If you see, then if you see D and EF, from state D, for x equal to 0, it is going to state E and the output is 0. And for x equal to 1, it is going to state F and output is 1. This is 1. From state F, for x equal to 0, we are going to state E and output is 0. And from state F, it is going to state F for input x equal to 1, the input. That means from this also you can eliminate one of the states. So let's eliminate F. So wherever we have F, we can replace it with D. So let's write again the reduced table. This is present state, next state. So we have A, B, C, D and E. For let's see whether we can still reduce the table. What is A? A, C, A, E, A. Now F has been reduced by D. Still if you look at AB kahin nahi hai, CD kahin nahi hai, AD, if you see now in this C and E, from C it is going to A, output is 0. From C it is going to D, for x equal to 1, output is 0. In the lower one, from state E, for x equal to 0 it is going to state A, output is 0. And from E it is going to state D, for x equal to 1, but the output. In this, both these states for x equal to 0 and x equal to 1, they are going to the same states, but their outputs are not same. For x equal to 1, their outputs are not same. So here we cannot do the reduction. Reduction of states at this point where they are going to same states for x equal to 0 and x equal to 1, but they are not having same outputs, we cannot reduce those states. So this is the final state table of your state diagram. So we have reduced 2 states, we have 5 states. Will it lead to state reduction? Let's see. Next is, after this, what is this? How do you assign the states? Since there are 5 states, you at least need 3 bits to do the state assignment. Either you can do state assignment, there are 3 ways. Either state assignment can be like A, B, C, D, E. I can write as binary. It can be a binary assignment. 1, 2, 3, 4, 5. Could be this. Similarly, in state assignment, it can be a gray code. 0, 1, 2, 3, 4, 5, 6, 7. This is another way. Or another way of assignment is one hot encoding. जितने assign states होंगे उतने bits होंगे. And out of those 5 bits, it will have one of the bits will be high. So this is called state assignment. So in a state table, if you want to do the state assignment, you can do it by 3 methods. One method is called binary coding. You can do the assignment using binary codes. Second is gray codes, and third is one hot encoding. When you want to do one hot encoding, the number of bits will be equal to the number of states. So how can you write this? What will be the reduced this? From A it goes to A, AB, 0, 0. From B it goes to C and D. From C it goes to A and D, 0, 0. From D it goes to E and D. G and F, they are both removed. This is the reduced state diagram. From D it goes to E on 0 and output is 0, and it remains within the same state for 1, 1. From E it goes to A on 0 and from it goes to D on 1, 1. So this is the reduced state diagram for a given state table. And if you want to do the assignment, then I can assign a binary number. This is A. For 0, it remains within the same state. For B, let's next state be this. If I do the state assignment, let this state be 0, 0, 0, this is 0, 0, 1, this is 0, 1, 0 as per binary. 1, this is 1, 0. So this is 1, and from this it goes to 0, 1, 0. From this state, C, it goes to D state. What is D? It is 0, 1, 1. then it goes to E, which is 1 0 0 for 0. So you can see for every input it goes from 0. If input is 0, it goes within the same state. If input is 1, it goes to this state. If input is 0, it goes to this state. If input is 1, it goes to this state. Now from this state, for input 0, it goes to this state. For input 1, it goes to this state. Now we are in this state. For input 0, it goes to this state. For input 1, it remains within the same state. Now here, for input 1, it goes to this state, and for input 0, it goes to initial state. So this is the state diagram with state assignment. This is how we do the state reduction and state time. Sometimes it may happen that for this also, अगर ये भी कम हो जाता, suppose this output was 0. Suppose. So this would have been reduced. So we are left with 4 states. That means E has been replaced by C. And we would have got 4 states. When you got 4 states, so you just need 2 bits to code to assign to the 4 states, because 2 means 2 raised to the power 2. 2 bits then, so the coding will be like this: 0 0 0 1 1 0 1. So this means when you have this as a circuit, this means 3 bits means you need 3 flip-flops. When you have that as a coding style 0 0, that means 2 bits means you need 2 flip-flops. And this can be drawn, this state diagram can be drawn with any type of flip-flop. It can be JK, it can be D, it can be T, it can be SR. There is no, you can say, restriction. But when you have JK flip-flop, JK excitation has more number of don't care terms. That means it will have a reduced circuit. If you draw this using a JK, it will be a reduced circuit. With T and D, it will have a bigger circuit, because T and D excitation tables, they don't have don't cares. And with SR also, in 0 0 state it is 0 cross, in 1 1 it is cross 1. So there also we have a few don't care, so that will also have a reduced circuit. We'll talk about those circuits in the next class. I think we can do good in that. I can draw for this circuit also, I can draw the circuit also if you want to. Let's draw it. We have time. तो ये reduction हो गई, अब हम इसका circuit बनाते हैं. So we have 0 0 0 for x equal to 0 and x equal to 1. It goes to 0 0 0, and x equal to 1, it goes to 0 0 1. What is the output? And what are the, let's have some, let's draw it with D A, D B, D C. This will, output will be same as a previous. I have to give more space to this. Not like this. It will be next state. Next state for x equal to 0 1 0 1, like this: 0 1 1 0 1. So I have something like all the states. All the states with x equal to 0 and x equal to 1. Then we have dA, dB dc. For x equal to 0, it goes to which state? Same state. For x equal to 1, it goes to next state. Now from 0, 0, 1, for x equal to 0, it goes to next state. For x equal to 1, it goes to next state. For 0, 1, 0, for x equal to 0, it goes to this state. For x equal to 1, it goes to this state. From 0, 1, 1, for x equal to 0, it goes to this state. For x equal to 1, it goes from this state. From 1, 0, 0, from x equal to 0, it goes to this state. For x equal to 1, it goes to this state. These are the values. And what is the DA? Our next state is always same as this. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1. So this is the next state equation is same as this equation. So what is Y? I want to draw the circuit for this. What is Y? What is Y? I want to write it down. I want to draw the circuit also. Let me get some space. What is this? Okay. What is the value of this Y output? It is 0. For this 1, it is 0. For this 0, it is 0. For this 1, it is 0. From here 0, it is 0. For this 1, it is 0. Then from here 0, it is 0. 1, it is 1. From here 0, it is 0, 1. This is the. So let's draw the K-map. What a K-map will have? It will have 4 inputs. Q3, Q2, Q1 of present state and X. So when you want to draw a K-map and want to get the next state equations, what is DA? What is DA? DB, DC, Y. So you have to make the K-map. What is DA? So you can see for 0, 0, 0, 0, it is 0. For 0, 0, 0, 1, it is 0. For 0, 0, 1, 0, it is 0. For 0, 0, 1, 1, it is again 0. For 0, 1, 0, 0, it is 0. 0, 1, 0, 1, it is 0. Then 0, 1, 1, 0, it is 1. For 0, 1, 1, 1, it is 0. Then 1, 0, 0, 0. You can take the other as don't care terms just to minimize the circuit, and we get this as the, what do you get? Q2, Q1, X. Similarly, I can get, take all the invalid terms as all the states which are not taken into account as don't cares. For this, it is 0, 0, 1, 1, 0, 1, 0, 1, 0, 1. So this is for dB, calculating dB. So we have these don't cares. I can have this as 1, this as second, and this as third, 3 quads. So this means Q2, Q1, Q3, Q1 X, and the third one is this and this, Q2 bar and Q1. This is DB. Then we have to find the third input DC, because there are 3 bits, so they need 3 flip-flops, 3 states. If you have 5 states, they can only be represented by 3 bits, not less than 3 bits. I have 0, 0, 0, 1. Again, I have to do the grey codes on both sides. These are the don't cares. DC. So 0, 1, 1, 1, 0, 1, 1, 1. It is 1. Rest are all 0. And 1, 0, 0, 1 is 1. So if you see this is 1 and this is another. So it is Q2, Q1X, Q3, Q into X. So these are the 4 equations of DA, DB, DC. You know that what is next state equation? For B, next state equation is same as DB. And for C, the next state equation is same as DC. So similarly, you can get a output for a Y. I have drawn this for drawing the state table, then I rub this off. I can have another K map just to get the output Y. Output Y. This is a K map. So for this 0, 1, 1, 1, 0, 1, 1, 1, it is 1. I think that is output Y. For DC, this is DC. This is not output, this is Y. What is DC? For 0, 0, 0, 0, it is 0. 0, 0, 1, it is 1. 0, 0, 1, 0, 0, 1, 0 is 0. 0, 0, 1, 1 is 1. Then 0, 1, 0, 1, and then 0, 1. So for this, I can have one octet, and this will equal to Q3, Q2 goes, Q1 also goes, DC is equal to basically X. Then what is the circuit? All the 3 are D flip-flops. They'll be clocked together simultaneously. So I'll give a clock to all. I can give a reset also. Asynchronous reset. Now what is DC? Is equal to X. So I can give these X. What is DA? Q2, Q1, X bar. So I have an AND gate. X bar. We have a X. So this is X. Q2, Q1. Q2, Q1 नाम देना है, और QA देना है. So this will be for DA. This is Q3. For B it is Q2. For C it is Q1. This is how we have drawn in the table. So what is Q2 and Q1? So this is Q2. And what is Q1? Let it be this. So this is Q2, Q1, X bar. What is DB? So this. What is Q2 into X? Q2 plus Q3 into X. So we'll have then Q2 bar into Q1. This is Q2 bar and this is Q1. Yeah, and it goes to this DB. So Q3 plus Q5 ये और ये finally आ रहा है. This will be given to. And what is Y? Y की value B है. So Y is What is Q3? So this is Q3. Q2. So I have Q2. And Q1. I have Q1 here. This is why. So this is how you can design a given, from a given set of specifications, you can draw the circuit, you can design a circuit, you can synthesize a circuit. So this is the whole procedure of synthesizing a circuit. You are given a set of specifications. From those set of specifications, draw the state diagram. From the state diagram, draw the state table. Reduce the state table by using the algorithm of state reduction. After reduction, do you see that is there any reduction in the number of flip-flops? If yes, then you can reduce those flip-flops. It may or it may not. Then from the reduced table, write the state table in complete form. You can design it using JK, D, T, anything. Write this table, whole table. From these, get the outputs for the flip-flop inputs and final output, and from that you draw the final circuit with which you are going to implement your design. You know the functionality of the design, you know the inputs of the design, you know the outputs of the design, how many inputs, how many, but you don't know the circuit. You want to design that circuit, and that is possible by this method. Thank you for today's lecture. We will start with SM tomorrow. FSM.